Yeah, I'm happy to be part of this conference. I'm not happy that I'm banned from the country, but just because of COVID. But yeah, so I was really looking forward to going back to Australia because I went to Jessica invited me to Melbourne. Sorry, it's a long day. It's been very okay. So she invited me to Melbourne maybe a few years ago, 3 or 4 years ago, and I had a fantastic time. So you can see I have a little picture of part of Melbourne here, and so I was really looking forward to going back. But this will have to do, and maybe someday we'll get to fly and travel again. Anyway, it was much faster to get to the third floor than to get to Australia. So, okay, so my talk is going to be very much the opposite end of the spectrum, very more pure theoretical, but let's get going. So, I'm a topologist, and so one of the things I study is knots and links. So these are related to things called low-dimensional topology and three manifolds and four manifolds in general. And I should say all of the work is joint with Chris Davis and Jung-Won Park. So I'm going to start from the very beginning because I assume that, there are probably people in applied math and such, and not everybody knows about knot theory. So let me start. It's kind of an easy subject because you can draw a lot of pictures. But it gets harder. But let's start off easy. So what is a knot? Well, it's just an embedding of a circle into space, but it doesn't have to be flat or anything. So the typical example everybody draws is the trefoil. So that's a standard trefoil. And there's also the unknot. There's figure eight. And anyway, there's an infinite number of distinct knots. And this talk will mostly be about links, but I'll try to motivate things with knots because they're a little bit easier. And so a link, all it is you have multiple knots, essentially. And so here's an example of the Hopf link. These are just the easiest to draw. But, they can be various number of components. You could put a bunch of components in. And I'm going to mostly focus on two component links for this talk, just because I don't want to have a bunch of subscripts and things. But okay, so why are knots and links important? Well, it turns out they are critically important in low-dimensional topology. Low-dimensional topology is the study of shapes and spaces that locally look like Euclidean space. They're locally flat, but globally they can be curved. In low-dimensional topology, what we mean is we're studying spaces that are dimension, 0, 1, 2, 3, 4. So I'm interested in 3 and 4 dimensions. And for 3 dimensions, one wants to study knots up to something called isotopy. And that just means that you can take, I guess I don't have a knot here, but at my house, they're all at school. But you can take the knot and you can just kind of move it around, but you can't cut it or break it. So, so you can see, here's some examples of knots, and they look very different. I want to point out something because maybe it's not clear to people. When I draw something like this, what I mean is that as you're moving along the knot here, you're going to go underneath this guy. So, so that's what that little crossing means. It doesn't mean there's an actual break. It's just indicating you're going under a bridge, let's say. So, okay. So these turn out to be all equivalent in 3 dimensions. I mean, this is called the unknot, so it's like the most trivial one. And then you can sort of just twist it, and, well, it turns out that this thing is also the unknot. And it may not be that clear when you first look at it, but you can start saying oh, well, look at this thing here. I can certainly, move that here and get the same knot. right? So I just sort of picked it up and moved it over, and you can just keep reducing things and eventually get down to the unknot, which we're not going to do. But what I'm interested in this talk is questions about four-dimensional topological spaces or smooth manifolds. And so if we're interested in properties of four-dimensional manifolds, which are truly the hardest dimension, and there's reasons behind it, but essentially comes down to 2 + 2 is 4. And I know that sounds silly, but it kind of is the reason. Okay, so we're really interested in something called concordance, which is now allowing our knots to sort of move through time. So you're allowed to do sort of certain moves as you flow through time. And I'll show you some example of these. These are called like movie moves. But essentially, you have an extra degree of freedom. So a lot more things can turn into the unknot, essentially, or the unlink. So, okay. So 2 links are called concordant. What does that mean? It means they bound smoothly embedded annuli in like R3 as you move through time. So at time equals 0. So here's a picture, is that, so this is a very schematic picture. So this is supposed to be like, well, you imagine it looks like R2, but imagine it's R3, and you have some, oh, that's not good. And so, you know, you have this link here, which has 2 components, red and blue, and these can be connected up at time 1 to L1 prime and L2 prime. And this is supposed to be, you know, just some annulus. So an annulus is just, you know, thickened circle. And you know, it doesn't have to be flat. These, I mean, I can't really draw it, but this is in 4 dimensions. So like this guy here could kind of wrap around this other guy. They could be knotted up. So now we don't just have circles knotted up, we have annuli that can be knotted up into 4-dimensional space. So you might think, well, this seems really hard because I can't really draw 4-dimensional things. And that's true, and that does make it a little bit harder, but there are tricks that we can do. So let me show you some examples of knots. So with a knot, you just have blue, right? There's no red. And so we want to find examples of knots where you can get from a knot that's not the unknot, like, you know, maybe the trefoil or figure 8 or something, to the unknot through 4 dimensions. Okay, so let me make a couple more. There's a lot of definitions in this talk. So a knot's going to be called slice if it's the boundary of a smoothly embedded disk in R3 cross 0, 1. So you can think about this drawn, like we draw this schematically, like here. Oh, sorry, I'm not going to do before. Oh, sorry. So, so basically you have your knot that's schematically in, you know, R3 cross 0. So here's your knot. And then you can ask whether it bounds a disk, and that disk is allowed to hang into 4 dimensions. So that's equivalent to being concordant to the unknot. So those are kind of things that are very interesting because they're the simplest types of knots in this 4-dimensional world. And so here's, I guess my time is going down. Okay, so can you change this through time? So it basically becomes unknotted. And you can imagine, what is the concordance? Well, if you have this guy, you can take a little tiny disk out the bottom, and that gives you the unknot, really. That is here. Okay, so so here is the examples I promised you. And you know, if you don't get anything out of this talk past these examples, that's fine. I mean, I think it's kind of cool to see these examples if you haven't seen them before. If you have, then you should just pay attention to the rest. So, okay, so this is an example. It's called a ribbon knot. And so what am I supposed to be doing? Well, I'm supposed to show you that this is slice. And Okay, so that means it's going to be concordant to the unknot, so we can find this way of maneuvering it. Or equivalently, you can say it bounds some sort of disk, and that disk is hanging in 4 dimensions in time. Okay, so how do we find this disk? Well, it turns out that this has a ribbon. This is called a ribbon, means it's a disk that's immersed. It may hit itself, but it has nice singularities. So let me draw the disk in green. Oh, actually, I think I'm going to use this. Where's the highlighter here? Okay, so this is some disk, but it does intersect itself. And then the intersection is going to be this. Oh, let me draw in a different color. So the intersection will be these 2 pieces right here. So you can see there's some self-intersection. It's a very nice singularity. And the singularities, you know, basically look like this guy. So this is that blue part. Okay, so this, it does not, that bounds a disk, but this disk is in 3 dimensions. And the problem is it's not embedded, like it hits itself. And so what we want to do is we want to get rid of those blue singularities and have no singularities, but we're allowed to use the fact that we can move in time. So what one does is you can take a small disk on this green disk. So I'm going to draw that pink guy. Okay, and then what you can do is you notice those pink guys, they form a bunch of disjoint disks. The boundaries an unknot, and what you can do is you can push those disks a little bit into 4 dimensions. So, you know, you have your disk up here. So yeah, you have this, and then we had the pink disk, which is here, and then it's just kind of hanging. And you can do this very, I mean, you can do this rigorously. I mean, it kind of seems like we're just like moving things around and things aren't smooth, but everything can be done nice. So basically you push this guy, the interior, into farther time, so into R4, which is the 4 dimensions. Okay, so that means that you basically have a disk. You take 2 holes, remove, and you put them in disks in R4, and so you're just going to get a smoothly embedded disk. This is slice. The other example, if you don't, oh, I guess I was supposed to draw it there. Okay. Another example is using these sort of movie moves, and this one is maybe kind of easier to see if you're, you know, if you like sort of thinking about level sets. So in this picture, I want you to think back to calculus, and I want you to think about multivariable calculus, where you have a surface that's inside of R3, and then you can look at R3 as R2 cross time, and then you can look at all the level sets, right? And when you look at those level sets, you end up getting bunches of circles, and you're getting, when you're looking at level sets, you're gonna get, you know, circles, and maybe you're gonna get some things like this, like if you have, you know, so, you know, if you take this slice, right, you're gonna get something like that. So you don't always get sort of like nice smooth objects that could have sort of singularities. Okay, well, we can do the same now in 4 dimensions. So imagine in 4 dimensions, you start with a knot at time 0. And then as you move through time, you're going to get a different picture, and they're going to have circles and singularities like we had before because they're surfaces. And then you're forming this like disk or the surface, and then what you want to do is then you just want to put all the pieces together. And so, right, if you know the level sets, then you can put everything together and have the whole surface. So this is the level set picture. Okay, so we're going to start with this knot. So we're going to think of this as time 0. So this knot happens to be called the 946 knot. It means it has 9 crossings, and it's the 46th one. There's nothing really special about that number. Okay, so then what we can do is we can start adjusting the knot. So what we're going to do is we're just going to like isotope it over a little bit like that. So what are you doing when you're sort of moving things around? You're not doing anything. You're just sort of taking your circle, you're sort of wiggling it around. But then the next step, you go and you can sort of hit a crossing. So bring the points completely together and you get this picture. So now you do have that sort of, wedge point. And then you can, so this is like, t equals 1/10 and t equals 1/5 or whatever. So we're just moving through time, and then you can desingularize it in the other direction, just like you would for a saddle point. This is the same sort of local model as a saddle. And then what you notice is this guy is actually 2 disks. I mean, this is actually, if you move it around like we did before in 3 dimensions, that is actually the unlink with 2 components. And then you can just cap those off with disks. Okay, so if you add those, I claim you get a disk, because what are you doing schematically? So let me move this. So schematically, what you're doing is you have this knot here, so that's time equals 0. Okay. And then you're going to create a saddle point. So let's say this is time equals 1 or something. Okay, so this is time equals 0. This is time equals 1/10. This part right here is time equals 1/5. And this is time equals 1. And you notice that, okay, so this is just, right, this is oh, I'm messing up the picture more. Okay, so this is, this is supposed to be something called a pair of pants, right? You just start with the circle, you have a saddle, and then you put the little feet on. And I like to call this a pair of pajamas instead of a pair of pants, because like the pajamas that have the little feet when you're a kid. So this is my pair of pajamas here. I guess it's a shirtless pair of pajamas, but okay. So anyway, so those are like 2 different ways that you can show that things are sliced. So this is basically 2 examples of things that are sliced, and they don't bound it. So they bound a disk in R4, but they don't bound disk in R3. All right. So what are we into? Okay, so I'm about halfway through. All right, so we are going to be interested in this equivalence relation called concordance, because that is the interesting relation that relates to 4-dimensional manifolds. So there's certain questions about conjectures about certain links being sliced, and it turns out is very important for like whether or not surgery works in dimension 4. It's a sort of big open question, and reflects on, you know, Friedman's work in the 80s, which you got a Fields medal. So some of this stuff is pretty hard, even though it's just like pictures. Okay. So we're going to study the set of M component links modulo concordance, and we're going to call that C upper M. If I don't ever put an M or a number, it just means I'm thinking of knots, one component links. So sometimes you can make this into a group, but it doesn't really matter. We're just maybe interested in the set today. And well, what is the sort of like trivial element? Well, there is an element that is a special element in there, right? There's the unknot. So even when you can't make this into a group, you still have monoid and everything. And so, you know, we're interested in when links are sliced, and we're also just interested in when two things are the same in this group. So that's a hard thing. Like for example, we had these examples of knots that were slice, right? But suppose I give you a knot and then I ask you if it's slice. And then you'll be like, well, aren't you the one that's supposed to know that? But okay. It might be really hard. So, I mean, if I give you something like the Conway Knot. So, oh, I forgot to draw it and I'm not going to be able to draw it in time. Okay, so there's something called the Conway Knot. So it has 11 crossings, so it's a very simple knot. Something called the mutant of the Kinoshita-Terasaka knot, which is known to be slice. And it wasn't known whether or not the Conway knot was slice until 2 years ago, when Lisa Piccirillo showed it wasn't slice. And up until that point, every invariant we had to detect sliceness of links and knots would not tell us anything about that knot. So the hard part about showing something is not slice is, well, you can't just say, oh, I can't, like, I looked for one disk and I couldn't find it, so therefore it's slice. You have to show that there's no possible way that you could ever have a disk. And so you have to have some sort of algebraic obstructions to that. You can't just, you know, you just can't say like, I tried 3 times and it didn't work. Okay, so how can we show a knot or link is not slice? So let me show you the easiest sort of thing, which for knots is called the sort of algebraic equivalence class of a knot. So you start with a knot. So here's a picture of the knot. That's my example I'm going to do. And then what we want to do is, we don't like topology because it's too hard, and sometimes we get the pictures wrong, whatever. So what we want to do is look at linear algebra, because we all like that. So, you know, if we want to do linear algebra, we better have some sort of matrix or bilinear form or quadratic form or something. And so that's what we're going to do. So turns out every knot has something called a ciphered surface, which is not at all unique. What it is, it's a surface that's in R3 whose boundary is the knot. So we're not allowed to go into 4 dimensions. This is all in 3 dimensions. No. Okay, so here's a picture of knot K. What is our surface going to look like for this guy? Well, let me just choose a nice one. There's going to be an infinite number of different ones, but I'm going to do this surface. Oh, I forgot I'm going to use this. Okay, so you basically can see that you have this disk with bands that you can color in. And as you look, this is going to be 2-sided, and there's a yellow side and a blue side, because this is going to be orientable. And what we're doing here is just, you take the band, you twist it 1 full twist, so it kind of turns over and then it goes back. So that is a picture of a ciphered surface. So that I'm going to call this guy sigma. And then from the ciphered surface, what we want to do is we want to find a matrix. And so what we're going to do is do something called the linking matrix. So let me take this picture here. So how do we, and quickly, what is the linking matrix? Well, you start with your ciphered surface and you find, if you know what it is, you find a symplectic basis for H1 of the surface. Basically what it means is like, take your surface and make it look like, you know, tying bands onto a disk. And then once you have that, then there are these core curves that go through the bands. So this, we'll call them, let's say alpha 1 and alpha 2. And then, and we can orient them some way, it doesn't matter. And then we can look at the linking, you know, the number of times of that one component sort of goes through the other. I mean, that doesn't quite make sense because they do intersect in this point. But then what you can do is resolve all the different ways. So there's two ways you can resolve that intersection, and one goes in one part of the matrix and one goes in the other. And then you can look at some self-linking, which is basically like the twisting that's going on here. You can see that this alpha 2 has a twist around it, and so that's going to be captured in the matrix. And so our matrix V is going to be sort of like alpha 1 with itself has a, well, okay, I don't remember if this twist is a plus or minus 1 twist, but like there's a negative twist. So let me just, let's pretend it's 1, or like, okay, let's just say plus or minus 1. And then 1, 0. Okay, so that happens to be the matrix, and these are pretty easy to figure out. So like an undergraduate can do this. And then what you can do is you have a matrix, and I think, okay, what are all the invariants I have in matrices? I have a lot. So, you know, maybe I can use those to get a bunch of knot invariants. Well, you know, they do have to satisfy some requirements, and they do have to satisfy even more requirements for slice knots. But you can still try to, you know, get some invariants. So the first, so the nicest invariant is something called the signature of the knot. And what you do is you take the signature of V. Well, that's a lie too, because what does a signature mean for a non-symmetric matrix? Okay, well, what you do is, oh, shoot, I already had a picture going. Okay, so I'm ignoring that. So what you can do is then take your matrix and add it to its transpose. Then it is symmetric. And then you have a symmetric non-singular matrix, and you can define the signature to be the number of positive eigenvalues of the matrix minus the number of negative eigenvalues. And it turns out that if it's not a slice, then that signature is always 0. More generally, instead of looking at just V plus V transpose, you can get an infinite number of Hermitian matrices by doing 1 minus omega V plus 1 minus omega bar V transpose, where omega is a complex number. Almost any complex number makes sense. And then it turns out these are all 0. So these give you an infinite number of different signatures. Okay, and so Levine in the 60s, he was really the one to start studying, you know, knot and link concordance. So what he did for knots, in fact, he did this in all dimensions, is that he defines some homomorphism from the knot concordance group, so it happens to be a group in that case, to something called the algebraic concordance group. In the algebraic concordance group, if you're an algebraist, you'll like, it's just going to be a Witt group of quadratic forms over Z. Okay, you probably don't like Z because Z is really hard, but you know, basically when you actually want to understand this group, you know, you have to look over Q, and then you have to look for torsion pieces, and you have to use, there's a lot of number theory. So this contains like, so this was classified by Levine, because most of the time that people are looking at Witt groups, you have to look at Witt groups over fields. And so basically you can get an infinite number of different Witt groups over fields and classify this group to be this. And so in high dimensions, there's a notion of being concordant. And in high dimensions, this map exists and it's always an isomorphism. And in fact, the Witt group of quadratic forms is not necessarily this, but it's 0 in like even dimensions and then something else. It's this in odd dimensions. Okay, so then you might think maybe this was an isomorphism in dimension 3, low dimensions, and it's not. So it was still another 10 years before Casson and Gordon showed that there are examples that are not algebraically sliced, so they're not in the kernel of this map, but they are not sliced still. So I want to point out that for people who are not familiar with quadratic forms, here is that what does it mean for something to go to a slice knot, the same as a slice knot in this group? Like, what does it mean to be 0 in that group? Well, it turns out you have some change of basis so that you can get something of this form. So you have a half block of zeros here. Okay, so that's what it means for the ciphered matrix to be algebraically sliced or for the knot to be algebraically sliced. Okay, and so like I said, Casson and Gordon, they prove that there are knots that are algebraically sliced but not sliced. So that means we need a lot more to understand knots than just this map. We're really interested in the whole kernel of it. Okay, and so the examples that Casson and Gordon did were basically you take this slice knot. So if J wasn't there, this would be the 946 knot and it would be sliced. But now what we're gonna do is we're gonna take that band, we're gonna take those two strings and we're just gonna tie them into a knot. And I think I meant to draw a picture of that and I forgot, and I don't think I have time. You just basically draw two parallel copies and of a knot, basically. And for people who are experts, you have to make sure there's zero linking between them. So, okay, so so that's knots, and we kind of understand knots pretty well, a lot more than links at least. Okay, so if we want to study links, and so can I have a few more minutes? Did we start like a couple minutes late?
We did. I think some of the groups may have to run off to
lunch, I will try to be very quick.
Great.
Okay, so what about links? Well, the nicest class of links are called boundary links because they look like a knot. It just means that a boundary link is one where each component bounds a disjointly embedded surfaces. So here's an example of a boundary link. When you flip over, you give this. Okay, and so boundary links are nice because now you're like, oh, I have ciphered surfaces, and so now I can form a really big matrix where I have different components, so something like this. And it turns out if a link is sliced, then we don't know that it's algebraically sliced. So that's an open question. In particular, so we want to ask, like, if a link is sliced, do we know we have a matrix of this form, which is which would be the sort of equivalent thing that we have for knots. So that's open, and I don't know the answer. Some other things you can look at for links are something called Milnor's invariants. There are a bunch of invariants that come from the lower central series, and they measure something about the longitudes of the link. And if they're boundary links, all these Milnor's invariants are zero. And if a link is sliced, then all the Milnor's invariants are zero. So kind of the point of studying boundary links is that you have all this information from the ciphered surface, and you'd like to know what kind of invariants you can get from it. The problem is not all links have ciphered surfaces. So what we want to do is study and understand boundary links first, which we still don't completely understand. But then what we want to do is say that every link is sort of related to a boundary link and sort of push across some of the concordance information. So that was started in the early 90s by Cochran and Orr, where they tried to push this through. So they showed that there are links where the previous invariants vanish, meaning the Milner's invariants, but they're still not concordant to any boundary link. So that's rather unfortunate. It means that if you just understand concordance of boundary links, it doesn't tell you everything. Well, we could ask, though, if we're not interested in the full slice problem, but a weaker notion, you could ask, is there some equivalence relation that relates any link with Milner's invariance vanishing to a boundary link? And so that's what we did. So it turns out there's some filtration of the group. You don't need to know what it is, but it has something to do with like higher order surfaces. Okay. So this is so we can use this to form an equivalence relation. For knots, I should point out that we sort of know the lower order terms pretty well, that RF invariant of being 0 is the same as being an F0. But the most important thing for this talk is this from here, is that being 0.5 solvable is the same as being algebraically sliced for knots, but it's not for links. And so we would like to know, when is a link algebraically sliced or when it's 0.5, and we don't know the answer to those. Okay, let me skip this. So anyway, so here's an example, here's a picture. This is an example of something called the Bing double of a knot. It's a boundary link. That's kind of hard to see. I don't have time to explain it. It is 0.5 solvable, but it's not algebraically sliced. So unlike for knots, these are not equivalent notions. Okay, so let me quickly get to our theorems. So we want to have some equivalence relation, and we're going to say it's n-solvably equivalent if they can co-bound in annuli, not in R3 cross I, but in something called the n solution, which you don't need to think about what it is. Sort of higher order surface stuff. And then, so my student a while ago, as a corollary to her thesis, it showed that, well, she didn't really study in this language, but every link is 0 solve equivalent to a boundary link. 0 solvably equivalent is a very, very weak notion. We'd like to get something that is a little bit stronger, closer to concordance. So we wanted to ask, you know, can you show that every link is sort of n-solvably equivalent to another link for all n? That would be a great theorem, but it's not true. Okay, so what we do know is the following. I'm going to skip this theorem because it's a little confusing. Okay, so what we were able to show some positive results. And so it turns out that I was talking about these Milner's invariants vanishing. That it's conjecturally equivalent to saying it's something called, the link is a sublink of a homology boundary link. So homology boundary link is sort of an algebraic condition that looks like a boundary link, but it's weaker. And in sublinks, you just remove some of the components. So it turns out that if you are a sublink of a homology boundary link, which should be all the ones with Milner's invariant 0 that are obstructed already, then L is 0.5 solvably equivalent to a boundary link. So the hope is then we can classify boundary links up to 0.5 solvable equivalent by using ciphered matrix or some moves like we did for knots, and then be able to understand the 0.5 solvable equivalence, which is a weaker concordance, but still tells you a lot more than we already know. The bad news is once you get past 0.5, things kind of are bad. So, so the sort of main theorem that's maybe a disappointing theorem, but is that for each n, there exists a link where the Milner's invariants are all 0, so we don't have those obstructions. They're going to be n-solvable, so n-solvable means that it is n-solvably equivalent to a boundary link because the unlink is a boundary link. But it's not going to be n.5 solvably concordant to a boundary link. So this means there are lots and lots of examples where you might have to go up and up and up, larger and larger n to be able to relate them to, or you might have to go, sorry, lower down to be able to relate them to boundary links. And anyway, that is the end. So thank you.
Thanks, Shelly.
I did go 5 minutes over, sorry. Well, okay, I didn't go 5 minutes over, it was started late.
Yeah. All right, great. I know that some of the groups have actual food coming in, and you're not tied to your Zoom like others. So if you do need to step out, that's fine. But if for those who have the time, if there are questions that you'd like to ask Shelly, that would be great. We have some time for that. Thanks. So Emily asks, can you say more about boundary links? How common are they?
Well, I mean, I don't know how you say common, but like, I guess it depends what you define as common. Like, you know, I don't know, you could put like some probability, some kind of measure of probability on the set of links by linking number or something. And so, I mean, every boundary link has to have linking number 0. So there's a restriction. So you could say that's like one, you know, that's a pretty limited condition. But then if you start with all links with linking number 0, which are things that I'm really interested in, I don't know. I guess this whole talk is about how common they are, in the sense of like, how can we relate any link to a boundary link, and what is the difference, sort of. But I mean, yeah, it's if I draw you if you draw a random link, it's probably not going to be a boundary link. But you know, you could take 2 split knots that are like far apart. Those are boundary links always. But those are sort of like very, very restrictive. They're not even like really links, because they're just knots. So, but anyway, I mean, it's a good question. I mean, it's actually interesting. There's a lot of obstructions and interesting things about boundary links in 3 dimensions. But yeah, I mean.
All right. Well, thanks very much again, Shelly.